Metrology and Material Science: Understanding Materials Through Measurements by Laura Vasquez. Hello, my name is Laura Vasquez, and this project explains 8 major topics in material science and connects them to metrology, the science of measurement. I use simple English and examples from my real experience calibrating medical equipment. Understanding materials help us understand why accurate measurements is possible and why engineers choose specific materials for safety and reliability. Goal of the project: explain 8 core concepts of material science, connect each concept to real applications in calibration and engineering, show how materials affect measurements accuracy and device reliability, present information in a clear visual way using pattern, demonstrate understanding through drawings, animation, and narrations. Atomic structure. Everything in material science starts with atoms. Atoms have electrons arranged in levels, and the arrangement decides how material behaves, its strength, melting point, and how it reacts. When I work calibrating medical equipment, I use tools made of stainless steel and aluminum. Their atomic structure explains why they feel different. Steel is stronger and heavier, and aluminum is lighter. Chemical bonding. There are 3 main chemical bonds: ionic, covalent, and metallic. Metallic bonds are important for medical equipment because they let electrons move easily. That is why copper wires conduct electricity so well and allow sensors to send accurate signals. Intermolecular forces. Intermolecular forces are small attractions between molecules. They affect melting points, how liquids spread, and how plastics bend. When I clean machines using alcohol, the way the liquids spread on metal versus plastic was because of intermolecular forces. Microstructure. Microstructure is how material looks on the inside. Some materials are crystalline, some polycrystalline, and some amorphous. Steel tools used in calibration have a crystalline microstructure that makes them strong. Plastics in medical equipment are amorphous, which makes them easy to mold. Defects in materials. Defects sounds bad, but not always. There are point defects, dislocations, and grain boundaries. Defects can actually make metal stronger because they can help the material stretch before breaking. In medical devices, we want controlled defects, not random ones, so materials stay safe. Phase diagram. Phase diagrams show how materials change with temperature. They help engineers choose the right alloy for strength, corrosion, resistance, or melting point. Aluminum alloys in calibration tools are chosen using phase diagrams so they stay stable and don't corrode. Diffusion. Diffusion is how atoms move inside a material. It affects heat treatment, corrosion, and how metals change over time. I saw in my calibration work that some metals rust faster. That is because atoms diffuse more easily in those materials. Mechanical properties. Mechanical properties describe how materials behave under force, strength, ductility, hardness, toughness, fatigue. All these decide if part will last. In medical devices, material must be safe and strong. For example, a connector on a blood pressure machine needs toughness to handle repeated use. And the conclusion is that metrology and materials science work together. When we calibrate medical devices, we depend on materials that are strong, stable, and reliable. This project helped me understand the science behind the tools I use and why accurate measurements depend on good materials.